Let us now modify our previous example slightly. We have the same two forces, F1 and F2, of known magnitude and direction that we had in example 1, but now F3 is of unknown magnitude and unknown direction. The problem statement requests that we find the force vector F3 of smallest magnitude such that the resultant force is directed along the axis of the I-beam. When you see a problem statement like this, requesting a value that minimizes or maximizes something, you may be conditioned from calculus to try to find a function of a variable, perhaps the angle alpha in this case, take a derivative of the function with respect to that variable, and set the result to 0 to find the value of the variable that minimizes the function. While that might be possible, it is far easier in this case to construct a graphical solution using a force polygon. When drawing force polygons, it is recommended to draw forces in the following order. First, forces with known magnitude and known direction are drawn. In the present example, F1 and F2 fall into this category, so we'll begin by including them in the drawing. Forces with either known magnitude or known direction are drawn next. No force in the present example falls into this category. Finally, forces with neither known magnitude nor known direction are added last. Force F3 falls into this category. You may wonder how we can sketch a force if we don't know its magnitude or direction, but we do so by using other information in the problem statement that guides our choices. We begin by adding F1 and F2 to the figure. To guide how we add F3, we use the information that the resultant force is to be directed along the axis of the I-beam. The dashed line in this figure gives the specified orientation of the resultant, so the tail of F3 is placed on the head of F2, and the head of F3 must terminate somewhere along this dashed line. We now consider all the possible choices of F3 that produce a resultant along this line. Three possibilities are shown here. The middle candidate is perpendicular to the line, so I'll add a 90-degree symbol at an appropriate location. I'll label the axis perpendicular to the resultant A, and label the axis through R B. Let the magnitude of the middle candidate be F3A. For all candidate vectors other than the middle candidate, there will also be a vector component along B, call it F3B, so that the magnitude of F3 is generally equal to the square root of F3A squared plus F3B squared. The F3A component is common to all candidate vectors, but the F3B component is variable. Since our task is to find the smallest magnitude of F3 to produce a resultant along B, F3B must be 0, the orientation of F3 is perpendicular to the resultant, and we immediately have half the answer to our problem. The angle alpha is equal to 45 degrees. What remains is to find the magnitude of F3. There are at least two ways to do this. From our previous exercise in example 1, we know the magnitude and direction of the intermediate resultant Q. We found that Q was equal to 867 newtons and made an angle of 108 degrees off the positive horizontal axis. Given the orientation of Q, the angle between Q and R is 27 degrees. And the right triangle formed from Q, F3, and R gives us F3 is equal to Q sine of 27 degrees And plugging in Q equals 867 newtons, we find that this is 393.6 newtons. Alternatively, you may notice that there is another 90-degree angle in this force polygon. Since F1 makes a 45-degree angle with the horizontal, we have another 90-degree angle between F1 and R. We can then note that this particular force polygon is actually a combination of a rectangle and a right triangle. We know from example 1 that the angle between F1 and F2 is 75 degrees. So the angle between F2 and a line parallel to R is 15 degrees. This distance then becomes F2 sine of 15 degrees, and we can say that F3 is F1 minus F2 sine of 15 degrees. We had F1 is 600 newtons and F2 is 800 newtons, and if we plug those numbers in, we end up with 392.9 newtons. You may wonder why these two expressions, which should be identical, are slightly different. In our example 1, we used relatively few significant figures, and so Q equals 867 newtons at 108 degrees are approximate values. If you go back to that example and retain more significant figures, you should find the corresponding numbers are actually Q equals 866.9 newtons at 108.05 degrees, and then F3 is Q times the sine of 26.95 degrees, and that in turn is equal to 392.9 newtons. From an engineering perspective, either answer is acceptable.